Hello everyone and welcome. I will be presenting continuously running genetic algorithm for real-time networking device optimization, a work I've done in collaboration with Doron Haritan and Natali Shechtman. So modern data centers, the performance of modern data centers rely heavily on the performance of the networking devices used to communicate between the different servers on the data centers. These networking devices have dozens of parameters that must be configured, and the different configurations of these parameters significantly affect the performance of the networking device and in turn affects the performance of the data centers. However, in modern data centers, we have a diverse set of traffic patterns and networking patterns that are going through the data set, and we can't expect one set of parameters to be optimal for all these scenarios. As the workloads are changing dynamically, this leads to the fact that by definition, one static configuration is always suboptimal, and this leads to many configuration issues that are raised by customers that are being caused because of configurations that are not aligned and are not optimal for the current traffic pattern. To solve this, we want to create an algorithm which would dynamically adapt the networking device parameters and adapt them to the currently running traffic pattern. This would lead to the best customer out of the box experience because the customer would get much better performance from its networking devices that are now optimally configured for the currently running traffic pattern, and will also save a lot of human resources that are spent today on finding static parameters that should be good for the customer and also debugging the bugs that are caused by bad configurations. However, any algorithm that is going to run and solve this problem of dynamically configuring the networking device needs to run directly on the networking device itself in order for it to respond and act fast enough and adapt the networking device on real time to the changing traffic patterns. This means that the algorithm is running on the networking device firmware. It is reading the performance counters or registers from the networking device and is setting the networking device configuration registers, and all of this is done in real time. And the algorithm itself needs to adapt to changing traffic patterns. This leads to three major requirements from any algorithm that is running on a networking device. The first one is that the algorithm needs to have high sample efficiency, which means it needs to adapt very fast to the changing traffic patterns, and it needs to find a better solution than the current one and not necessarily the best solution. Second, it has to be dynamic. It means that it needs to be constantly running. It does not need to find static parameters, but actually find dynamic parameters that are constantly changing in order to fit the currently running traffic pattern. And finally, it needs to have very low computational costs, since the networking device computation and storage are both usually very low, and the algorithm need to use a little part of them in order to run and perform well. To solve this, we present here zero-touch tuning, a continuously running genetic algorithm, which is fast, simple, and is able to run dynamically on the networking device. What we do is we take the very basic genetic algorithm and do some slight modifications to the algorithm to meet all the requirements. First, we'll just recap the basics of genetic algorithms. So a genetic algorithm has four basic stages. First one is the creation of a population, which is usually done in the initialization of the algorithm. Then we calculate some fitness score for all the population and select the top performing subset of individuals to continue for the next stage. Then we create a new population by mutating specific individuals or creating new individuals by doing a crossover between two or more individuals from the current population. The algorithm continue running until some stop criteria is being met, where we get the best set of parameters and use them. So ZTT is doing the basic genetic algorithm with some modifications. The first step of creating the initial population is exactly the same. And the second step as well. We calculate the fitness score for the individuals we have and keep the top performing K individuals at our populations. I would say here that we also keep in the side the score of the best performing individuals for later use. In the third step, this is the first step that we do some modification to the algorithm. When we do the mutation, we check for each new individual that we create, we check its score compared to the score of the best performing individual that we calculated on step 2. If the score of this individual is better than the one of the best, we insert it to the population of K-best and remove the lowest performing individual from the K-best individuals. Then we do a step that is called refresh. This means that we actually recalculate the score of the best performing individual because as the traffic patterns changes, the score of the best performing individuals might be completely different. And since we use it to insert new individuals to the population, we need to recalculate it for the algorithm to perform faster. Then we do the crossover phase, and here again we do the crossover, but we always take the new individuals and compare it to the score of the best one, which was calculated on step 4, and insert it to the top K individuals. On step 6, we do the refresh again. And finally, we go back to step 3, to the mutation phase, and repeat the entire process again. And as you can notice, we have completely removed the stopping criteria from the algorithm, which make it dynamic. We always do the selection. The selection here is ongoing. This makes the algorithm much faster, so we don't have a special dedicated selection phase. We do a continuous selection. And finally, the algorithm is very simple, as it uses only the basic operations of a genetic algorithm, which is selection, mutation, and crossover, and even those are done in their most simple form. And this leads to an algorithm that is simple, dynamic, and fast, and can work and run directly on a networking device and adapt it to match data changing traffic patterns. To test the algorithm, we wanted to create a setup that is as similar as we can to something that is running on a real data center. For this, we created a physical setup which has physical networking interconnect devices, some virtual servers that emulate some more NICs, and a physical switch. The algorithm and the other algorithms that we compare our algorithm to are running directly on the NIC firmware and are being used the same ways that they are going to be used in a real data center. To test the algorithm, we created a very diverse set of traffic patterns that is running through this setup and is supposed to cover most of the cases of real traffic that is running at the customers. The traffic tests are different in the numbers of the hosts that are participating. Not every host on every NIC is participating on every test. The bandwidth from the host is varying, and we also do a thing that is called overloading, which means that some of the hosts are getting a bandwidth that is larger than the one that they can actually get. We also notice here that only the physical NICs are running the ZTT, while the virtual NICs emulate NICs that does not have ZTT running on them. This is something that can happen on a real data center as well, and we cannot count on the fact that all the NICs are running our algorithm. Our goal here is to maximize the bandwidth and minimize packet drops, which is a requirement that is usually coming from customers, and this improves the application performance on the data center. So the first result we want to show you is a movie. We are showing here several tests that are running continuously with different traffic patterns, and we can see on the gray line the best static parameters that are found by experts and the performance of them. And then on the green line, we see the performance of the ZTT when we turn it on, and we will see that the ZTT is able to bring the bandwidth higher and decrease the drop rates as expected. We will also see that unlike the static parameters, ZTT is changing the different knobs on our case dynamically and adapts them to the running traffic pattern. And you can clearly see how the traffic patterns is changing, the bandwidth is changing, the drop rates are changing, and nevertheless, the ZTT is able to achieve better performance compared to the static parameters. The bandwidth is on average higher on both the RX side and the TX side, and the drops is significantly lower in all cases, and you can see how the knobs are changed dynamically throughout the test. And to get some numerical results, what we did is that we compared ZTT against two other algorithms. One other successful search algorithm was one is called simulated annealing, and another one is called recursive random search. And what we show here in this table is that we compare each of the algorithms, the performance of each of the algorithms to the performance of the static parameters that are found by experts on all the tests. And what we did is we ran each test of the 20 for 30 seconds. We ran them consecutively, and we ran this scenario for several times to get statistical significance. And what we can clearly see is that ZTT is able to outperform all the other algorithms and is able to significantly outperform the static parameters. The other algorithms are also able to outperform the static parameters, which shows that static configuration is indeed not good when the traffic patterns are changing, but ZTT has a significant advantage over other algorithms like simulated annealing and recursive random search. What we can also see is that the refresh mechanism we showed previously is indeed improving results and making the algorithm faster and able to get better results. And this shows the importance of this mechanism for adapting to changing traffic patterns. We also test two more important metrics, the convergence time and the stability. For convergence time, we mean that we want to see how many individuals each algorithm needs to check before it reaches a performance which is better than the one of the static parameters. And what we can clearly see here is that the ZTT is able to reach better performance much faster than simulating annealing in an RRS. And this is a very important metric since the traffic patterns may change very fast. And an algorithm that does not able to respond fast enough will not be able to improve the performance of the networking device. Stability is also very important because even if on average we get better performance than the static parameters, we want the performance itself to be stable because unstable performance can be detrimental to the performance of the networking device. Here as well, we can see that ZTT is able to reach a better stability compared to the other algorithms. To conclude, we showed that small changes to a basic genetic algorithm can make it dynamic, simple, and fast. We showed that ZTT can be used to tune the networking device parameters, tune it online, and get better performance in terms of increased bandwidth, decreased drop rate, and faster convergence and more stable performance compared to other search algorithms. ZTT, due to its simplicity and responsiveness, can run directly on the device firmware. It also has low computational cost and low storage cost. ZTT also works out of the box, does not require domain expertise, and improve results of the networking device significantly. Finally, we do hope to see things similar to ZTT in many more use cases that needs dynamic tuning of parameter. Thank you.